Today we will talk about developing a project schedule. Our first topic is developing the project network. The project network is a crucial tool for planning, scheduling, and monitoring project progress. It is developed based on the information gathered from the work breakdown structure, WBS, and serves as a visual flowchart of the project's job plan. The network illustrates the project activities, their logical sequences, interdependencies, and often includes the start and finish times as well as the critical paths through the network. Developing project networks requires time and resources, but they are highly valuable. Networks are easily understandable by others as they present a graphical representation of the project's workflow. They can be easily modified in response to unexpected events, such as delays in materials, allowing for quick assessment and adjustments to the entire project. These revisions can be efficiently communicated to all project participants through electronic means like email or project websites. Project networks offer additional benefits and insights. They serve as a basis for scheduling labor and equipment, facilitating communication and coordination among managers and groups involved in the project. They provide an estimate of the project's duration, helping avoid arbitrary deadlines and allowing for more accurate planning. The network also identifies critical activities that should not be delayed if the project is to be completed as scheduled. It highlights activities that can be considered for compression if there is a need to meet a deadline. Furthermore, project networks minimize surprises by enabling early planning and facilitating corrective feedback. They are often considered a significant portion of the planning process by project managers due to their perceived importance in the field. Overall, project networks are invaluable tools that contribute to effective project management by supporting decision-making related to time, cost, and performance objectives. From work package to network. The project network is a visual diagram that represents the sequence, interrelationships, and dependencies of activities required to complete a project. It is developed based on the work breakdown structure, WBS, which provides the work packages used to build the activities in the network. Activities in the network represent elements of the project that consume time, such as work or waiting, and can include one or more work packages. Integration of the WBS and project network is crucial for effective project management. However, this integration can often fail due to different groups defining work packages and activities, as well as a poorly constructed WBS that lacks deliverable/output orientation. To ensure continuity, it is important for the same people who defined the WBS and work packages to develop the network activities. Project networks provide the project schedule by identifying dependencies, sequencing, and timing of activities, which the WBS does not cover. The primary inputs for developing a project network plan are the work packages. Each work package is defined independently and has specific start and finish points, required resources, technical specifications, and cost estimates. However, the dependency, sequencing, and timing of these factors are not included in the work package itself. As you see, this figure illustrates how information from the WBS is used to develop a project network. The lowest level deliverable, such as circuit board, is represented, and cost accounts, e.g., design, production, test software, indicate project work, responsible organization units, and time-phased budgets for the work packages. Each cost account can include multiple work packages, Sequencing tasks from all work packages with measurable work is necessary to develop the project network. Care must be taken to include all work packages in the network, and activity time estimates are derived from the task times in the work package. Once the early and late times for activities are computed, the manager can schedule resources and time phase budgets with specific dates. Overall, the project network is an essential tool for visualizing and managing the sequence, interdependencies, and timing of project activities, integrating the WBS with project scheduling, and facilitating effective project management. In project management, terminology plays a crucial role in facilitating effective communication among colleagues who work together on projects. Here's an explanation of the key terms used in building project networks. 1. Activity. An activity is an element of the project that requires time to complete. It may or may not require resources. Activities can involve people actively working or waiting for certain events to occur. For example, waiting for contracts to be signed, materials to arrive, government drug approval, or budget clearance. Activities typically represent one or more tasks derived from a work package. Descriptions of activities should use a verb/noun format to clearly define the action and the deliverable, for example, develop product specifications. 2. Parallel activities. These are activities that can occur simultaneously if the project manager decides to schedule them that way. They do not have a strict sequential dependency and can be executed concurrently if it is feasible and beneficial for the project. 3. Burst activity. A burst activity is an activity that is immediately followed by more than one activity. It is represented by having multiple dependency arrows flowing from it, indicating that it has multiple successors. 4. Merge activity. A merge activity is an activity that is immediately preceded by more than one activity. It is represented by having multiple dependency arrows flowing to it, indicating that it has multiple predecessors. 5. Path. A path in a project network refers to a sequence of connected activities that are dependent on each other. It represents the flow of work from the project's start to its completion. 6. Critical path. The critical path is the path or paths in the project network that have the longest duration. It is the sequence of activities that, if delayed, would directly impact the project's overall duration. If any activity on the critical path is delayed, the project will be delayed by the same amount of time. Identifying the critical path is crucial for project scheduling and helps determine the minimum duration required to complete the project. Understanding and using these terms accurately and consistently allows project managers and team members to effectively communicate and analyze project networks, identify dependencies, sequence activities, and prioritize critical tasks for successful project planning and execution. Okay. When developing project networks, it is important to follow certain rules to ensure clarity and consistency. Here are 8 basic rules to keep in mind. 1. Networks flow typically from left to right. Project networks are typically developed in a left-to-right format, where activities are arranged horizontally from the left side representing the project start to the right side representing the project end. 2. Precedence rule. An activity cannot begin until all preceding activities it depends on have been completed. Activities in the network should be connected in a logical sequence, ensuring that dependencies are properly defined. 3. Arrows indicate precedence and flow. Arrows in the project network represent the flow and precedence of activities. They indicate the relationship between activities and the direction of work progression. Arrows can cross over each other without affecting their meaning. 4. Unique activity identification numbers. Each activity in the project network should have a unique identification number or code. This helps in distinguishing and referencing activities accurately throughout the project planning and execution stages. 5. Activity identification number order. The identification number assigned to an activity must be greater than the numbers assigned to any preceding activities. This order ensures that activities are arranged in a logical and sequential manner. 6. No looping or recycling. Looping, where a set of activities repeats or cycles through itself, is not allowed in project networks. Activities should have a clear start and end point, and they should not create loops that could lead to confusion or infinite cycles. 7. Avoid conditional statements. Conditional statements, such as if successful, do something. If not, do nothing, should be avoided in project networks. Activities should be defined with clear start and end criteria without relying on conditional logic. 8. Common start and end nodes. When there are multiple start or end points in a project, it is recommended to use a common start node to indicate the clear beginning of the project in the network. Similarly, a single project end node should be used to indicate the clear ending point. By adhering to these basic rules, project managers can create well-structured and easily understandable project networks that accurately represent the sequence, dependencies, and flow of activities in a project. Activity on Node AON is method for developing project networks. 1. AON method dominance. Over time, the availability of advanced computer graphics has improved the clarity and visual appeal of AON method, leading to its dominance in project network plans. 2. Building blocks of AON network. In the AON method, activities are represented by nodes or boxes, with rectangles, boxes, being the most common form in recent years. Dependencies among activities are depicted by arrows between the boxes, indicating the sequence and logical interdependencies of activities. 3. 3 basic relationships. 3 relationships need to be established for activities in a project network. A. Predecessor activities. Activities that must be completed immediately before a given activity. B. Successor activities. Activities that must immediately follow a given activity. C. Concurrent or parallel relationships. Activities that can occur simultaneously while a particular activity is taking place. 4. Burst activity and merge activity. A burst activity is an activity from which multiple arrows burst, indicating that multiple activities immediately follow it. A merge activity is an activity that cannot begin until multiple preceding activities are completed. 5. Milestone activities. Milestone activities indicate significant accomplishments in the project. They are often represented by merge activities, where multiple activities must be completed before the milestone activity can begin. 6. Construction of AON network. The AON network is constructed by identifying the dependencies among activities and drawing arrows to represent the relationships. The order in which activities are drawn is based on their precedence relationships. 7. Importance of time estimates. Adding time estimates to the network allows for project scheduling, resource allocation, determining project duration, and estimating completion time. Time estimates help in planning, scheduling, and controlling the project effectively. By using the AON method and considering the relationships between activities, project managers can develop a visual representation of the project network, which helps in understanding the sequence, dependencies, and estimated time required for each activity, as you see in this figure part A. There are 3 activities A, B, and C. They are depicted in a sequential manner, where activity A must be completed before activity B can begin, and activity B must be completed before activity C can begin. In the same figure, part B shows that activities Y and Z can only begin after activity X is completed. Activities Y and Z can occur concurrently if desired, but activity X must be completed first. This type of relationship is known as parallel activities. Figure part C illustrates that activities J, K, and L can occur simultaneously if desired, and activity M cannot begin until activities J, K, and L are all completed. Activities J, K, and L are parallel activities, and activity M is a merge activity that requires multiple preceding activities to be completed. Last one. Figure part D, activities X and Y are parallel activities that can take place at the same time. Similarly, activities Z and R are parallel activities. However, activities Z and R cannot begin until both activities X and Y are completed. These examples demonstrate the fundamentals of the AON method, where activities are represented by nodes, and their dependencies and relationships are depicted through arrows. The network can be developed by accurately including all project activities, their dependencies, and their time estimates. OK. This slide describes the network computation process, which involves determining the start and finish times of activities in a project network. The process consists of 2 passes: the forward pass and the backward pass. Forward pass, earliest times, 1. Early start, ES. This determines the earliest possible start time for each activity in the network. 2. Early finish, F. This calculates the earliest possible finish time for each activity based on the early start time and activity duration. 3. Expected time, T. This indicates the estimated time for the entire project to be completed, considering the longest path, critical path, determined during the forward pass. Backward pass, latest times, 1. Late start, LS. This determines the latest possible start time for each activity, considering the project completion time and the activity duration. 2. Late finish, LF. This calculates the latest possible finish time for each activity based on the late start time and activity duration. 3. Critical path, CP. The critical path represents the longest path in the network, and any delay in activities on this path will delay the overall project completion. 4. Slack or float, SL. This indicates the amount of time an activity can be delayed without affecting the project completion time. Activities on the critical path have 0 slack. The forward pass starts at the first activity and progresses through the network, adding up activity times along each path. The longest path determines the project completion time and represents the critical path. By performing the forward and backward pass, project managers can determine the earliest and latest times for activities and identify the critical path. This information is crucial for project planning, scheduling, and resource allocation. As you see, this is a diagram of a project management process for an automated warehouse order picking system. It outlines the different stages involved in creating the system, along with the dependencies between these stages. Here's a breakdown of the activities. Define requirements. This is the first step and involves outlining the needs and functionalities of the order picking system. This includes determining the type of items the system will handle, the throughput required, and the budget allocated for the project. There are no preceding activities for this step. Assign team. P. Once the requirements are defined, a team is assembled to oversee the design, development, and implementation of the system. This team may consist of engineers, project managers, and warehouse specialists. Assigning a team can be done concurrently with defining requirements. Design hardware. C. In this stage, the hardware components of the system are designed. This may involve designing shelving units, conveyor systems, and robotic arms. This activity depends on defining the requirements. Code software. D. This involves writing the software programs that will control the warehouse order picking system. The software may instruct robots on how to move around the warehouse, operate picking arms, and manage inventory data. Coding software depends on assigning a team. P. Build and test hardware. E. The designed hardware components are built and then tested to ensure they function according to specifications. This activity depends on designing the hardware. C. Develop patent request. F. If the order picking system includes any novel inventions, a patent request can be developed at this stage. This activity can be done concurrently with building and testing hardware, since they are not dependent on each other. Test software. G. The written software is thoroughly tested to identify and fix any errors. This activity depends on coding the software. D. Integrate systems. H. Once the hardware and software are built and tested, they are integrated together to form a cohesive system. This activity depends on building and testing hardware. E. Testing software. G. And developing a patent request. F. If applicable. This diagram represents the process for developing an automated warehouse order picking system, outlining various stages and providing estimated completion times in weeks for each stage. Define requirements. 10 weeks assign team, 5 weeks design hardware, 25 weeks code software, 20 weeks build and test hardware, 50 weeks develop patent request, 15 weeks test software, 35 weeks integrate systems, 15 weeks. In forward pass computation, we are talking about the process of the forward pass in project network computation. Here's a step-by-step breakdown. 1. Start with the first project activity, e.g., Activity A, and its early start time, usually set as 0 at the project start. 2. Add the activity duration, do, to the early start time to calculate the early finish time, F equal ES plus do. For example, if activity A has a duration of 10 workdays, its early finish time would be 10. 3. Identify the activities that are dependent on the completion of the current activity, A in this case, known as successors, e.g., activities B and C. The successors can only start once the current activity is completed. 4. Set the early start time for the successors as the early finish time of the current activity. In this example, Activities B and C would have an early start time of 10. 5. Repeat steps 2 to 4 for each successive activity, calculating early start and early finish times based on their predecessors' early finish times. 6. For merge activities, activities with multiple predecessors, select the largest early finish time among the immediate predecessor activities to determine the early start time of the merge activity. 7. Continue the forward pass until you reach the last project activity. 8. The longest path in terms of early finish times represents the project completion time and is called the critical path, CP. Activities on the critical path have zero slack or float. 9. The early finish time of the last activity represents the expected time, T, for the entire project to be completed. By performing the forward pass, project managers can determine the early start and early finish times for each activity, identify the critical path, and estimate the expected project completion time. In the process of the backward pass in project network computation, here's a detailed breakdown. 1. Start with the last project activity, e.g., activity H, and set its late finish time, LF, equal to the early finish time, F, of the last project activity or the imposed project duration deadline, if applicable. In this example, the LF for activity H is set as 100 workdays. 2. Subtract the activity duration, do, from the LF to calculate the late start time, LS equal LF minus do. For example, if activity H has a duration of 15 workdays and the LF is 100, the LS for activity H would be 85. 3. Identify the activities that are dependent on the completion of the current activity, H in this case, known as predecessors. These activities will have their late finish times determined based on the current activity's late start time. 4. Set the late finish time for the predecessors as the late start time of the current activity. In this example, activities E, F and G would have their late finish times set as 85, 85 and 85, respectively. 5. Repeat steps 2 to 4 for each preceding activity, calculating late start and late finish times based on their successors' late start times. 6. For burst activities, activities with multiple successors, select the smallest late start time among the immediate successor activities to determine the late finish time of the burst activity. 7. Continue the backward pass until you reach the first project activity. 8. The late start time of the first project activity represents time period 0. 9. By performing the backward pass, project managers can determine the late start and late finish times for each activity, which provide information on the latest possible start and finish times without delaying the project completion. 10. The difference between the early start and late start times, LS minus ES, or the difference between the early finish and late finish times, LF minus F, represents the slack or float of an activity. Slack indicates the amount of time an activity can be delayed without affecting the project completion time. Once the backward pass is completed, project managers have the information on early start, ES, early finish, F, late start, LS, late finish, LF, and slack for each activity. This information is essential for project scheduling, resource allocation, and identifying critical activities that have zero slack. Okay. Now determining slack or float times. This slide explains the concept of total slack in project management. Total slack, also known as float, refers to the amount of time an activity can be delayed without affecting the project end date or any imposed completion date. Total slack is computed by finding the difference between the late start (ls) and early start (es) times of an activity, or between the late finish (lf) and early finish (f) times of an activity. ls minus es equal sl or lf minus f equal sl. Total slack indicates the flexibility or leeway an activity has in terms of its start and finish dates. 4. Activities with total slack can be delayed without impacting the project's overall timeline. If an activity on a critical path uses its total slack, the early start times of all activities that follow in the chain will be delayed, and their slack will be reduced. Coordinated planning is necessary when using total slack in order to manage the impact on subsequent activities. The critical paths in a project can be easily identified by examining the activities with zero slack, LF minus F equals 0 or LS minus ES equals 0, or activities with LF equal F. The critical path is the network paths, with the least amount of slack in common. However, if the project finish activity has a different LF than the F found in the forward pass, e.g., due to an imposed duration date, the slack on the critical path will not be 0. In such cases, the slack on the critical path will be the difference between the project F and the imposed LF of the last project activity. Negative slack occurs when the critical path is delayed, indicating that the project is behind schedule. Critical activities, which are activities on the critical path, typically represent about 10% of the total activities in a project. Project managers closely monitor critical path activities to ensure they are not delayed, as any delay in these activities will directly impact the project's overall timeline. By understanding total slack and identifying the critical path, project managers can focus their attention on the activities that have the most significant impact on the project schedule and ensure they are properly managed and completed on time. Okay, let's talk now about practical considerations. Network logic errors in project management refer to violations of the logical rules and principles governing project network techniques, potentially compromising the accuracy and effectiveness of planning, scheduling, and control. Common errors include conditional statements. Project networks should not incorporate conditional statements as they disrupt forward and backward pass calculations. While projects may deviate from plans, the network assumes a specific activity sequence, with revisions made as necessary. Looping. Returning to a prior activity violates logical precedence relationships. Properly constructed networks maintain ascending activity identification numbers, preventing perpetually repeating paths. Activity numbering. Each network activity must have a unique identifier, commonly ascending numbers or letters. Gaps between numbers allow for future additions. Numbering occurs after completing the network due to its complexity. Use of computers. Project management software aids in network development and analysis, but requires a solid understanding of project management principles. Input errors are common, necessitating skilled project managers to identify and rectify mistakes. Calendar dates. Assigning calendar dates to activities is vital for scheduling. Software or manual methods can be used, aligning workdays with the project network. Automatic date assignment is common in software programs. Multiple starts and multiple projects. Interconnected projects require a common start and finish event in the network to avoid dangler paths. Pseudo or dummy activities tied to a shared node enable different start dates for each project.
Thank you for watching. If you liked this video, please like and subscribe to channel.